in the last class we looked at how distances are briefly extracted from 2D nosy and the NOE based idea that NMR structure determination by NMR is basically a model building approach. So, now let us look at this 3D NMR experiment called 3D nosy HSQC, which is basically very important experiment when it comes to proteins. So, if you recall, in a protein we do isotope labeling. So, if you have an isotope labeled protein, then we have to obtain distances based on this experiment in the 3D nosy. That means you need an N15 labeled protein and a C13 labeled protein. So, there are 3 types of this 3D experiment. We will see the pulse sequence shortly. There are 3 types of 3D nosy experiments which are routinely used in protein NMR. So, one is called N15 nosy HSQC, C13 nosy HSQC, and now in C13 we have 2 types. One is for the aliphatic spin systems, that is for the side chains of hydrophobic hydrophilic amino acids, and you have another C13 nosy which is for aromatic spin system, that is in the case of phenylalanine, tyrosine, tryptophan and so on. The reason these two are different because the chemical shifts of aromatics and aliphatics are widely different, both in terms of proton and in carbon. In carbon typically aromatic comes around 140-130 ppm, whereas aliphatic comes between 0 to 60-70 ppm. So, therefore, it is difficult to do both aliphatic and aromatic HSQC nosy or nosy HSQC in a single experiment. Therefore, this 3D is now split it into 2 parts. One is exclusively dedicated for aliphatics and one is dedicated to aromatics. So, before we go into this, we should recap one thing in nosy which I had mentioned briefly yesterday, that you have to now look at this intensity versus mixing time. So, what is the intensity concept here? So, this is a schematic of a nosy spectrum. This all of us know this is a 2D nosy where this is called a diagonal peak and these are the cross peaks between the different hydrogen atoms. So, now if what happens to this intensity? That is a volume. Remember, when I say intensity, it means peak volume as shown here. So, now as we vary the mixing time in a nosy experiment, the peak volume will keep increasing, but after some time the peak volume starts decreasing. Now, this is very interesting. Why does it have to decrease, increasing the mixing time? The reason is that when the long mixing time is used, what happens is a cross peak between 2 atoms starts appearing even though the 2 atoms are not close in space, means they are greater than 5 to 6 angstrom, but still you will start seeing a peak. Why does that happen? That happens because of a phenomenon known as spin diffusion. So, let me illustrate with a picture. Suppose I have an atom A and B and C. Suppose the distance between this is 5 angstrom and distance between this is 3. So, the total distance between this is 8. So, obviously between A to C I do not expect any cross peak, but from A to B I am getting a cross peak and from B to C I am getting a cross peak. So, what will happen is when I excite A, although C is far away, it can first transfer to B, and if I use a longer mixing time, slowly B will get transferred to C. Okay. So, this is why the B intensity starts decreasing like this, because it is now whatever had come from A is getting passed on to C, whatever means the population, the polarization, whatever had come because of the close distance is getting further transferred to C. So, the intensity of B or the cross peak between A and B starts decreasing, but cross peak between A and C starts increasing, because now the A magnetization is going to C through B, but A and C should not actually directly transfer because they are far away. So, this intermediate spin is now helping to transfer from A to C, but then the cross peak between A and C will start appearing in a spectrum, and that will tell us that will be misleading, because we will interpret that this cross peak means it is less than 5 angstrom, and that is not correct, because that could be because of spin diffusion. So, how do we know that a peak is because of spin diffusion or a correct peak? The only way is that you vary the mixing time and see if the peak intensity is decreasing or increasing. Okay. So, if the peak intensity in the initial mixing time if increasing and later it starts decreasing, then the peak is basically going to spin diffusion peak. Okay. So, this is an unfortunate problem which happens very many times. So, typically that is why what we do is we try to restrict the mixing time to smaller values. Typically for proteins you do not want to go beyond 100, 80 typically is the average used for medium sized proteins. 60 millisecond mixing time is used for a larger protein, but not more than 100, because then more than 100 the peaks which you start seeing could be because of this effect, and that will be misinterpretation of data. For small molecules, that is organic molecules, which we are not looking at in this course, but there you will have to use a little longer mixing time, and typically that is in the range of 150 to 300. So, therefore, as mentioned here, mixing time has to be carefully chosen to avoid spin diffusion peaks, because this can cause wrong interpretation of distance between atoms, because you may think that this is somewhere 5 angstrom because there is a peak between A and C, but actually it is not, it is a longer distance. So, your structure will become wrong. So, this point has to be carefully, with experience it comes, and mixing time has to be appropriately chosen. So, now let us look at the pulse sequence of a 3D NOESY. Before I look at 3D NOESY, we will again look at 2D NOESY first, because all 3D experiments, remember, are based on 2D. So, 3D experiments are essentially an extension of 2D NMR experiments in general. So, now let us see 2D NMR 2D NOESY experiment. Here we saw that you have 3 90-degree pulses. The first pulse brings the magnetization to the xy plane, and then the magnetic spin starts evolving. During that period we gather the chemical shift of each nucleus hydrogen atom, that is cosine omega T1 or sine omega T1. Then this pulse inverts the magnetization and it goes to z axis or minus z axis, all the protons. This is something which I am repeating a recap from the previous part of the course. So, I am not writing it here, I am just mentioning it, that you invert the protons, and then when they go back towards z axis during this mixing time, that is tau mix, they start transferring the polarization to each other. And the transfer of polarization is called the NOE effect. Now, that transfer from A to B or B to A or A to C and so on is then, whatever has transferred is further excited with another 90-degree pulse, because remember during this period it is along z axis. So, we cannot detect a signal unless we bring it to the xy plane, and that is brought by this 90-degree pulse. Then we detect the signal, and that is the final detected signal. So, what is important is the polarization transfer which happened during this period is captured in the cross peak between T1 and T2. So, this was the basic idea of NOESY, 2D NOESY, which I have done a very brief mention. You can go back to the first part of the course or read the several standard books which give a very good and detailed explanation of this pulse sequence. So, now let us see from here how can I extend this pulse sequence to a 3D NOESY experiment in proteins. So, what we do is the following: we start from the same experiment first. So, this is the same repetition of the last slide, 390-degree pulses, there is a T1 evolution and then a mixing time. Then what I do is, after I bring this to z xy plane, this last pulse, remember, brings the magnetization to the xy plane, this is the NOESY part. We then continue with the HSQC part. So, this entire part here is an HSQC pulse sequence. So, if you recall the HSQC experiment we discussed again in the last part of this course, first part of the course, we saw that HSQC is basically through inept. First you have the inept part, then you have the evolution part of the heteronucleus. Now, this heteronucleus can be either carbon or nitrogen, it can be anything, it does not matter whether it is carbon or nitrogen, this the same idea is applied to both. And then we have the reverse inept, and we detect the signal finally. So, this is actually T3. So, let me correct this here, this is T3, okay, because there are 3 dimensions in this experiment. The very first is T1, the heteronucleus evolution here is T2, and then proton evolution again because we are detecting protons is T3. So, let me explain now how things go in this figure, how the magnetization is taken further or taken. Let us start from this picture here. Now, let us go back to this. So, when we excite the proton by 90-degree pulse, let us say this is our molecule, this is a schematic drawing of a molecule. So, this is hydrogen I, J and K. So, when I excite the protons first by this pulse, this first pulse here, all the hydrogens are excited because this is not a selective pulse, it is a pulse which is applied to all the protons. So, all of them are excited and they start evolving during this period in with their chemical shift. So, it is called cosine omega, it can be sine also, it does not matter, but I am just writing it as cosine. So, cosine I, Hi, Hj, Hk, T1, each of this is during T1. Now, during the mixing part, these magnetizations are now exchanged between the different hydrogen atoms. So, Hj will give some 5% of its magnetization to Hi, Hi will give 5% to here, 5 or 6 or 1%, all depends on the distance between them, it depends on the strength efficiency of transfer between them and so on. Similarly, Hi and Hk will also transfer to each other. So, they will exchange some few percentage of magnetization to each other. But remember 90% is kept with themselves, 90 to 95% of magnetization is actually never given to anybody, only 5% exchange goes on, even less than 5 sometimes. So, this is this tiny transfer between magnetizations is what we try to detect. Now, after the mixing is over, then we have come to the HSQC part. In the HSQC part you have this inept, what is shown here, where we transfer the magnetization to this own carbon. So, let me write down here, we are transferring to directly attached carbon. Okay. Now, once we do that, we can then excite this carbon here, and during this period T2 we evolve the carbon now. So, I, J, K, because all 3 carbons are now coming from this respective I, J, K. So, all 3 will evolve during this period. Then during this last part, that is reverse inept, we transfer it back to proton. Again there is a slight correction here, it should be T3. So, we transfer it back during this inept to proton, and what you detect during T3 is again back to this proton. So, here what we have done is we have gone back to this proton, we have gone back to the proton. So, we had only come to carbon to get the chemical shift value. Once that is done, we go back to proton, the same protons from where it came. So, I, J and K. Now, in the next slide I will show you how we can get the correlations. Now, what kind of information and correlation we get in a 3D NOESY spectrum, but we have to now carefully look at this slide, understand how the magnetization has gone from one nucleus or one spin to another nucleus or a spin. Okay. So, this is again the last part, that is this part what I showed in bottom is repeated here. Okay. But one thing, if you recall, in a NOESY our goal is not to transfer magnetization within amino acids. For example, if this is one amino acid, we are not interested so much in within the atom like this, within the amino acid. And why is that? Because this can also be done with a TOCSY. If you recall, TOCSY achieves magnetization transfer within a network of coupled spins. That was the definition of TOCSY, and that is, this is a network of coupled spins, means a family, and each amino acid we saw is like a family of protons. So, we do not need this transfer through NOESY, TOCSY can do that. What we are actually interested is basically a transfer to a long order. So, let us first understand how this transfer has happened. So, you can see that this is the 3 hydrogen atoms I, J and K within the amino acid, okay, that has now transferred to this. But because of this interatomic transfer here, what has happened is whatever was on the H has come to I, whatever was on the J has also come to I. This is because of the NOESY. So, let me write down here, this is because of the NOE effect. So, because of the NOE effect, all of these have exchanged their magnetization. Therefore, all these 3 terms are transferred to HI, because HI is of course the same as HI. So, it is the same, as I said, 90% is with HI, but whatever came from J, this would have come from J, this part, because this modulation is transferred to J, from J to I. Similarly, this modulation from K to I. So, that means these entire 3 are actually transferred to the I. So, therefore, when I is evolving as Ci, these 3 now are connected, okay, or correlated with this Ci. Then similarly, this 3 will be also correlated to this J. Why? Because again if you see here, Hi is transferring to Hj, Hk is transferring to Hj, and Hj is retaining 90% with its own. So, again all the 3 are transferred, are kept on Hj, and when Hj evolves, this omega C Hj term will be connected to these 3 terms, and same thing for the Hk or Ck, because again Hk retains 90% on its own, that is the diagonal peak, but the cross peak are coming from I to K, J to K. So, these modulations, that is these terms, are connected to these term also. So, all 3 with all 3. Then each of this gets connected with this, that is through inept. So, that is just Ci to Hi, Cj to Hj, Ck to Hk. Here there is no cross terms, cross meaning there is no term between Ci and Hi or between Cj and Hi, because this is inept, is only direct transfer. Okay. So, you see this is how what happens, that all the 3 hydrogen atoms here, the modulations are connected to each of these 3, and each of these 3 are connected to their respective protons. So, if you look at this in this manner, you can say that we have correlated. So, remember this word correlation. So, we have correlated the chemical shift of I, J and K with Ci and Hi. So, this is the first arrow here. If you follow this arrow, this first arrow, this here and this here. Then we have also correlated again the same 3 nuclei with Cj and Hj, which is the second arrow here. And we have also correlated again the same 3 atoms with Ck and Hk. So, you see we have correlated all the 3 with all the 3 each other. Okay. So, this is basically the idea, that you are correlating with each other. So, you are getting all possible combinations of connections. Okay. So, these correlations, so this can be thought of as correlation omega, omega, omega I, omega j correlations will be seen in the spectrum as a peak. So, when we say a peak in an NMR spectrum, a peak can be diagonal peak or it can be a cross peak. So, what is a diagonal peak? Diagonal peak is a peak where you have the same repeated 2 times or 3 times. So, you can see here Hi is repeated. So, this correlation, that is this correlation becomes a diagonal peak, and these correlations and this correlation, they are cross peaks. This is very important to keep in mind, what is a diagonal peak and what is a cross peak. Okay. So, now what is the advantage, what is it, why is this big deal? The big deal here is diagonal peak do not carry any distance information in a NOESY spectrum. Why? Because they are correlating one atom with the same atom. So, there is no question of distance between the same atom to same atom. But cross peak carry information of the distance, because the intensity there will now depend on the distance between Hi, Hj. For this case it will depend on distance between Hi, Hk. So, you see the cross peaks are important and not the diagonal peak, but we cannot help, diagonal peak will always be present because the transfer does not take 100%, 90% to 95% is retained on the same atom. Similarly, in this combination here you will see Hj, Hj here. So, that is a diagonal peak, but these two are the cross peak, these two combinations are giving us the cross peak. In the same manner here HK and HK, this combination is a diagonal peak, whereas these two are the cross peak. So, therefore, one should be able to figure out what is a diagonal peak, what is a cross peak, and therefore, of course, in the spectrum you can very easily find out, because a diagonal peak will be a huge peak about 99% in intensity compared to a small cross peak which will be very weak. So, in principle you do not need mathematically to know, but it is good to understand from where diagonal and cross peak comes, but in a spectrum it will be very straightforward, very easy to identify what is a diagonal peak and what is a cross peak. So, this is how the Nosy spectrum will come in a 3D manner. This is what I showed. As I said, we are only illustrating for a single amino acid or within the amino acid. I will show you shortly for a longer distance how it works. I mean for a cross peak to a remote atom or a long range atom. Right now let us focus what we get within a amino acid. So, as I said, this information can also be obtained from TOCSY, but I am using this only to illustrate how does a Nosy work, 3D Nosy work. So, you can see the 3D Nosy spectrum will be something like this, where you have 3 dimensions. So, H1 will be the 3, remember F3 means frequency or time domain is what we saw in the time domain part, but in a spectrum it will be always frequency. So, this axis is carbon, but remember it can as well be nitrogen. Why? Because if you go back in this program, let me go back to this pulse program, here it can be nitrogen or carbon or nitrogen. So, I can do the same thing, all the things same for nitrogen also. So, everywhere carbon will become nitrogen. So, there is no reason why it should be only carbon or nitrogen. The only differences will be in the inept part, because if you recall, inept depends on the J coupling. So, J coupling between carbon and hydrogen is different from J coupling between nitrogen and carbon. So, therefore, that is the J coupling difference we have to tune for the difference in carbon and nitrogen, but the mixing time will be the same whether it is carbon Nosy or nitrogen Nosy, the proton mixing time will be same. So, this is how the spectrum will look like approximately, and now you can see for each plane, this is just for example for these 3 atoms. If I am looking at the HI chemical shift, I am looking at this part here. So, this basically, let me show you a correlation, this corresponds to this corresponds to this, and this corresponds to this. Okay. So, for this combination here, for a given HI in a T3 value, look at this here, HI in T3 and CI in T2, CI in T2. For that combination, that is a plane. So, we can say this is like a plane, this is the plane we are looking at. Then in that plane we will get 3 chemical shift along the F1 direction or T1 axis, which is why, because it is T1. So, all the 3 chemical shift I, J, K are coming. So, you can say that now here which is the diagonal peak, this is the diagonal peak. Although it does not locate it diagonally, but this is a diagonal peak because it is HI and HI in the same plane. Now, if you look at this plane here, this corresponds to this set of correlations, and in this set this now Cj Hj plane. So, we are in the Cj Hj plane. In that plane I am seeing along this axis, along this Hj chemical shift, 3 peaks again coming from I, J, K, here I, J and K. Similarly, for this plane I am getting correlations to I, J and K, but I am in the Ck Hk plane, I am in the Ck Hk plane. Okay. So, this is how the correlations are is seen in a Nosy HSQC. Now, we can analyze this in a strip manner. So, we can cut out strips like this and display it in a computer and also analyze like that. So, this is how 3D Nosy HSQCs are analyzed in a strip manner, and this is something we will see like in a 3D spectrum. So, this is how it is. So, this is what I showed you, the 3D plane mode, and this is some spectrum of a real molecule. So, the Nosy HSQC of some molecule is like this. So, what we do is a base. So, if you look at this here, look at this F2 F3 is nothing but an HSQC. That means, if I take the top view of this projection of the spectrum, it is nothing but a HSQC. So, I can write it here, it is nothing but an HSQC. This plane is an HSQC. What kind of HSQC? It can be either carbon HSQC or it can be nitrogen HSQC. And along this dimension, in the third axis, I am seeing cross peaks. So, if you recall, in the previous slide we looked at HI, HJ, HK, etc., and that is what is HI, HJ shown here. Okay. But one thing, if you notice, again I will go back to this slide, as I mentioned, we are all looking within the same amino acid. Example was shown like that. Okay. So, I said that this information, this spectrum also can be obtained in TOXI HSQC. So, TOXI, if I take a TOXI HSQC 3D, which we saw in the 3D part in the previous part of this course, the first part, we saw the similar pattern is obtained there also. So, then what is the difference? The difference actually is, in a NOESY we will see additional peaks, not only the peaks from one amino acid, that is the same amino acid, we will also get peaks from far away amino acid because of the NOE effect, and that effect is something what we are looking for. We are not interested in getting peaks from the same amino acid, but we are interested in getting peaks from the neighboring amino acid, from far away amino acids, because those are the ones which carry the distance information. And this is something which we will see in the next class, that how a far away amino acid gives correlations to peaks in the same amino acid spectrum in a 3D NOESY spectrum, and from there we will see how we can extract distances and calculate the 3D structure of the protein. We will see that in the next class.